Hello everyone. In this video I want to show you two other parts of Fusion 360 simulations. One is modal analysis or vibrations, and the other one is buckling, and I decided to use this I-beam that I designed because it's appropriate for both of them. So here we go ahead and see first, as I always said, you need to make sure you have geometry, which you do, and you need to make sure you have material. And you see that the material is stainless steel, so the material is there. Now here for vibration I have rotated it and laid it flat, although you don't really have to, but I think this is kind of more understandable. Now we go to simulations, and then we go to steady, new steady, and then we do modal frequency. And this is all about finding natural frequencies and mode shapes, so you really do not need to have any load. All you need is a constraint. And here I'm going to use a cantilevered beam, so I fixed this end entirely. So now it's a cantilevered beam, and you see it's already green because you are ready to go. And so here I'm going to create the mesh, right? So that's the mesh. Let's generate it, and then we are going to solve, because that's all you need to do is to find the natural frequencies and mode shapes. Now here is a little bit too big for a mesh size, so I would rather look at the mesh here. I think this is a little bit too big, so let's see if we can make it smaller. And remember that we can always turn on the option to, if you remember, look at the refinement, right? So here we put it at medium. And now I guess we are ready to solve. So I have done one already, but let's do another one so you just can see it. And I just call it natural frequencies and mode shapes cantilevered beam. Okay, and here the simulation starts. It should not take really too long because this is a simple simulation. Okay, the results are in, and of course we can change the deformation. So here it's adjusted again. It's not the actual one, and of course you can do animation. Right, so this is the first mode shape here, right? Let's have it two ways, and for speed let's make it fast. So that is the first mode of vibrations here that you can see, and the frequency is 86 hertz. It's a lateral displacement, right? And then so you see the displacement is the total right now. Then we can go to mode 2, which is 150 hertz. And again, if we look at this one, let's see. So this is up and down deflection instead of left to right with the higher frequency. Then we go to next one and next one. This is the twisting mode. So you can see that this is the twisting vibration, higher frequency this time, 328. And then here is the second mode of lateral vibration, right? So you see now the shape is more complicated, right? There is a node here. And then you go to upper modes for basically up and down vibrations like this. And then upper modes for twisting vibrations and like this one. And so it went up to 8 modes. And it calculated 8 modes for you, and it shows all the frequencies and the mode shapes. This last one is not a deflection or twisting. This is the change in the length. This is basically the extension and the shrinkage, or the basically longitudinal vibration that you can see here, and the frequency is very high. Okay, so this is a simple vibration modal analysis. Of course, this is not force vibration or anything. This is just pure free vibrations. Okay, and then of course we can do a similar thing here, and we can do a similar thing And this time we can go ahead and do a buckling analysis. But for buckling, I would like this to be vertical, although again, you don't have to. So here we go and edit this, and we find the sketch, right click and redefine the sketch plane, and we try to put it on the vertical plane like this. There we go, and now it's good. So now we should be able to go to simulations, and then we pick the buckling here. So let's see what happens if we make it a cantilever again. So we go here under constraint and structural constraint, and we go down here and we pick this and we set all the conditions of motion to 0. And then you definitely need to put some load so it knows how it is going to buckle. So I'm going to put some structural load, and I'm going to put it right there. And let's say I use 200 Newton, or let's use a little bit more, maybe 500 Newton. So it is going to compare the number that comes from the Euler formula to this number and kind of give you a safety factor. So you see it's good now. And again, you can always check the mesh, or you can go here and look at the setting. And if the mesh is small, you can, or big, you can always go and check it. And if there is any local mesh or anything you want to do, you can do that as well. And then go ahead and look at the buckling here. So I call it cantilevered beam buckling, and let it go. And again, I stop the video. Once the simulation is over, I'm gonna show you the results. Okay, the results are in, and you can see that there are 3 modes of buckling that are showing. This is mode 1, where the load that is needed to start the buckling is 2700 times the load that we applied. So we have a huge safety factor here, of course. And we can look at the deflection. So this is about this axis. And then we can change it to the other one, and again we can look at the animation. This is about the other neutral axis, right? And then finally we have this guy here, which is basically this mode of buckling. Okay, so at minimum we have about 2600 times the load. And remember, the load, if you go and look at it, it was basically this force here, and this force was 500. So we can apply a lot more load than that before this beam is going to start buckling, and clearly we are absolutely safe in terms of the beam buckling. So hopefully these 2 videos were useful to you. You learn how to perform free vibrations analysis or modal analysis, as well as buckling on an object, which in this case it was an I-beam, a cantilevered beam. Thank you so much. I'll see you in the next video.